So Bohr, what's made Bohr's theory so special? Okay, before I go to Bohr, let's talk about the the atomic spectra. So let's give a little understanding of the atomic spectra. Okay, um, in atomic spectra, we have the Balmer series. Okay, we Balmer used hydrogen gas and observed the wavelength of the spectral lines, which were colored, fits the formula. Give you the formula: 1 over lambda. Okay, we will not prove just in higher levels that this formula will be proved. Okay, this Balmer, he observed that the wavelength of the spectral lines fits, which were colored, fits this formula. Okay, this R is the Rydberg constant. Rydberg constant, and lambda is the wavelength in nanometers. Okay, so we also okay, this is the N1 is the energy level. Sorry, N1 is the chill is the initial number of lines in the series. Okay, we have Lehman, Bauman, Pascal, bracket and font. Okay, okay, let's go down a little bit. Okay, okay, so this is the Balmer's equation. Yes, a little while. Okay, so this is the Balmer's equation. You have the Balmer. Okay, let me. Okay. 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 Let's take a break. So I'm just looking forward to continue with this. Okay, then the Bohr's theory. So we haven't talked about the Balmer's theory. Balmer's series. We have Lehman. I have Lehman. Okay. We have Lehman. We have Balmer. We have Pascal. We have brackets. We have font. So, and in all this, we have the N1. We have the N2. Okay, and this N1 is 1. This 2, 3, 4, and so on. This 2, 3, 4, and 5. So, this go to 4. This 4, 5. This 5, 6. This 6, 7. So and so on and so forth. So this is the atomic spectra, and in this atomic spectra we have energy levels. Okay, these energy levels we talked about, we will talk about the emission of energy, how energy is emitted or how energy is absorbed. Okay, why do they move, and what can be the theories behind it, the conclusions we'll find from them. So we go to Bohr's theory. Okay, but like I said, Bohr combined quantum theory and classical physics and drew the following conclusions. Okay, the electrons can only be allowed in permitted orbitals. It cannot be found in permitted orbitals. It cannot be found in permitted orbitals, and okay, the electrons move in circular orbits around the nucleus, but are in a stationary state. Okay, they move in circular orbits around the nucleus, but are in a stationary state. That means they do not radiate energy as classical theory predicts. Okay, they move in a circular orbit around the nucleus, but in a stationary state. That means the electron does not radiate energy when in this orbit. Okay, and as associated energy, okay, and as associated energy in a definite orbit. Okay, they don't emit energy. They don't, like the classical theory predicts, they don't radiate energy. They just move in circular orbit. Okay, and remember, these electrons are currently found in permitted orbitals, in allowed orbitals. Okay, and these circular orbits are quantized energy levels. Okay, the greater the energy of the electron, the larger the radius of its orbit. Alright, and let's go to the quantum theory. Okay, but we have this formula. Okay, like I said before, permitted orbitals, electrons couldn't be found in permitted orbitals. Okay, they just move in circular orbits around the nucleus, but are in a stationary state. Okay, that means they don't radiate energy as they move around. Like, for example, let's say we do it like this. This is the nucleus, these electrons, as they move around, according to classical theory, they radiate, as they move around, they radiate energy. But yeah, we found out that they don't radiate energy in quantum theory, because according to what Bohr said, after combining the classical and quantum theory, discovered that they don't actually radiate energy. Okay, and these circular orbits are quantized energy levels. The greater the energy of the electron, the larger the radius of its orbit. As a result of the circular motion, electrons will have angular momentum. Okay, so this mass, this velocity, and this radius. Yn is the principal quantum number. Okay, we also find out that it's equals to h over 2 pi. So h over 2 pi is equals to mvr. Okay, so and h over 2 pi is equals to h. So say nh is equals to mvr, and so just is the formula. Okay, and that's according to Bohr. So So in this theory, it said that electron can gain or lose energy only by jumping from one permitted orbit to another, thus entering a new stationary state. Electron can gain or lose energy by moving from one permitted orbital to another. Permitted orbital, thus entering a new stationary state. Now, when an electron moves from one stationary state to another, the amount of energy it gains or loses is exactly equal to the energy difference between the two states. When an electron gains or loses energy, when it moves from one stationary state to another, the energy it loses or gains is exactly equal to the energy difference between the two states. So it comes to this. Electron gains or loses energy. The energy it gains is exactly equal to the energy difference between the two states. So we have this. Remember Balmer? Okay, this one, the energy here is greater than this because it's the first energy state, second energy state. Okay, so let me give a brief description just for better understanding. Okay, n is equals to 1, n equals to 2, n1, n2. So I'll be, if electron moves from here to here, or moves from here to here, that's just what it's saying. This is stationary state, it's another stationary state. As electrons move from one stationary state to another, it gains or loses energy. Okay, and the energy it gains or loses is equal to the energy difference, this, between the two energy states. Is the energy difference between the two energy states. Okay, we're going to prove formulas. We're going to I haven't talked about this. We won't go into the uncertainty principle, the Broglie's assumptions, this wave particle duality. We just talk about it. We won't go deep into it. Talk about the time independent Schrödinger equation, higher levels of chemistry. Talk about the de Broglie's. We talked about the wave particle duality of an electron. Is just saying light waves are made of particles, and de Broglie reason that if particles are composed, if light is composed of particles and yet showed wave-like properties, their matter will behave in the same manner. So it just related them, and he gave birth to the uncertainty principle that you can actually electrons are or atoms are, you can find them. There's a certain way you can find them. You can't actually find them. You can't say this is where I'll find an electron. Okay, that's why it's uncertain. Okay, it's impossible to know exactly both its momentum and position of an electron at the same time if that electron has wave particle duality. That's what the uncertainty principle is saying. It's impossible to know both the position and the momentum of an electron if the electron has wave particle duality. So let me just give the equation to show it. You can't tell where this electron is if you know the momentum. And if you know the momentum, you cannot tell where. And if you know the position of the electron, you can't tell its momentum. So it's what you're just saying. It's simple equation. You have this position and momentum. Okay, this is just it. So you can't really tell where the position is, where the momentum. Okay, this is Heisenberg uncertainty principle. Okay, This is the Eisenberg uncertainty principle. Eisenberg uncertainty. Uncertainty principle. You can't really tell where the electron is, and knowing the position at the same time, and knowing the momentum at the same time. Okay, so it's just what the principle is. Okay, we won't go to limitation of Bohr's theory. Okay, we're going to talk about the Zeeman effect, the Stark effect. Yeah, that's one limitation to Bohr, which is very important. One limitation is just that you can't explain the wave particle duality of an electron. That's what it says. That's very important. Bohr's theory can actually explain the wave particle duality of an electron. It's not in agreement with Heisenberg uncertainty principle. Okay, because according to Bohr's theory, electrons have known radius and orbit. That is to say, we have the exact location of the position and momentum. The exact location of the electron and its momentum. Okay, and Heisenberg principle doesn't agree with Bohr's theory. So that's one of the limitations of Bohr's theory. They can't explain the wave particle dual nature. It can't be applied to atoms or ions with more than one electron. Okay, that's a multi-electron existence. It can't explain when a spectral line gets split up into 5 lines in the presence of electric field. It can't explain the Stark effect. Okay, and these okay, that's just it. And if we want to explain the problem of uncertainty or solve that problem, we need to talk about the Schrödinger equation, and which course is limited. It doesn't go that far. Okay, in higher levels of chemistry we'll talk about that. Okay, so let's solve some questions. Okay, 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 and for a question it's very very easy. So okay, in the second part of this topic we talk about the quantum numbers and other principal quantum number as a mutual quantum number and the rest. But yeah, we will talk about, but now we will focus on atomic number, mass number, and isotopes. Before we go into that, I'll talk about the ionization energy. Just briefly, ionization energy. This is the this is the energy needed to completely remove an electron from a gaseous atom or molecule in its ground state. Or we can call it ionization potential. Is the energy needed or required to completely remove an electron from a gaseous atom or molecule in its ground state. Okay, forming a positive ion. Okay, let's say this, and this is gas. So we have ionization potential. So gas plus electron, just and just that means if an electron, let's say let's pick aluminium for example. All right, aluminium. Okay, let's see, aluminium. Okay, yeah. Let's see, yeah, yeah, 3 plus. Okay, and 1 is 2. Boys coming out of that, never seen men away. Okay, 13 is 2 p6, 3 is 2, 3 is 2, 3 p1, and okay. Okay, that's that for aluminium. So you know that the ionization energy here, like we said, is the energy required to lose, or let me say in a more explicit term, energy required to lose the most loosely held electron in the outermost orbital of a gaseous atom. Okay, is the energy required to lose the most loosely held electron in the outermost orbital of a gaseous atom. So we would know that here the ionization energy to remove this will be so much more smaller, and to remove one of this, okay, or to remove another one of this. Let me put it in levels so you get what I'm saying. Okay, 3 pp1 yes. Okay. We don't have to go here. The first ionization energy. Let's say is 578 kilojoules per mole a second. 1817 kilojoules per mole. Two 745. Okay, first, second, third. 2 come here, 2, 3. Okay. Kilojoules per mole. Alright, so to explain this trend, for aluminium to lose 1 electron, okay, an atomic shell, it requires 578 kilojoules per mole. Compared to this, to lose 1 electron from a fully filled orbital, you know, if it loses an electron from S orbital, 1 electron will be left, but S orbital is completely filled and very, very stable, so you require a higher number of energy. And as we will explain in further classes, as an atom gets smaller, or as a move across the periodic table, in the trends of the periodic table, as you move across the periodic table, an element gets smaller. As you remove an electron, it gets smaller. So does the screening effect. The screening effect is the ability of the inner electron to shield the ability of the inner electrons to it's also called the shielding effect of the inner electrons to form a protective wall. Okay, they create more effect, they come together more. All right, so it will be so much more difficult to take one electron from here, which is half filled, because it has become smaller here. This one has become smaller. This is much more smaller than this. This is smaller, smallest. Okay, so it will be very, very difficult to remove this electron from here. The reason for the increase. Okay, it's this one is connected to this. This is connected to this. Alright, to remove this one, it will be very, very hard, very, very difficult. Alright, so to form 2p6. And to remove this one, remove one from here. Let me make it this way. So for easier explanation, okay, to remove one of these from here, it's very, very difficult. Not compared to this, removing this one, because it's much more closer to the nucleus. Alright, it's more closer to the nucleus, even with half filled, because half filled is still stable. Okay, don't know how stable as fully filled, but it's still very, very stable. It's very easy to remove this one from here. Why? Because it's never up to half filled. P, a p orbital, it contains M3 degenerate, so it is currently named as PX, PY, PZ. So it's never half filled. You need 3 electrons here to be half filled, but it's 1, so it's much easier to remove this electron from here than this. Okay, so the energy required to remove the most loosely held electron in the atomic shell of an orbital is called the ionization energy. That in simpler terms. Alright, so we'll go to okay, that's that for today. From next class we'll continue from the atomic number, mass numbers, isotopes. Then we'll go to the quantum numbers. We'll do some few calculations on the atomic theory. We talk about the Bohr's model and everything, the Balmer series, just 1 or 2 calculations. Then go to the quantum numbers, the SP, DF, the shells, KLMN. So by we are done for today. Thank you very, very much.